for years and years, we've been used to working in analog. You turn up the knob on the control panel and you put out 9 volts onto the track and the loco goes fast. You turn the knob down a bit to 6 volts and it goes slower. So the values they're putting onto the track are analog. They're constantly changing as you rotate the knob. But more and more things are moving over to digital for model railways and general electronics. When it comes to ordinary numbers, it's fairly straightforward, you know, but digital is different. Digital is looking at information being stored in single little bits of information. So whether we're looking at DCC, whether you're looking right now at me on your monitor, whether you're watching television or whatever, although you're seeing lots of information getting put to you, behind the scenes, it's just a whole string of digital highs and lows values. And these values are called bits. They're either +5 or 0 volts, maybe they're +12 or 0 volts or whatever. They only have 2 real states. They're either off or on, sometimes called 1 or 0. They're called bits, which is an abbreviation of a binary digit, binary meaning only 2 states. It's either high or low, off or on. To make life a bit simpler for handling them, we tend to aggregate them into blocks. And you'll see down the bottom, we have a byte, which is just a set of 8 separate bits lumped together to give us more intelligence. So we're going to look at how we arrive at that, how we store these numbers inside computers, inside our modules, and also how we pass these numbers back and forward. The top list shows you we move numbers about all the time inside computers and inside our radio and television. In terms of merg, you'll find them inside servo 4 boards to operate servos. They're inside DCC systems. They're inside C-bus, EasyBus, and all the PIC chips that we program. We move them around in different ways, as we'll look at a bit later. So no matter what you're looking at, you may be looking at a picture of Mona Lisa on the screen. And this beautiful detail behind it, again, as I said, is nothing but a whole collection of nothings and ones. Starting from where we know, we were born with 10 fingers, and therefore we developed the decimal system. And it goes what we call base 10, everything's in tens. So the numbers go from nothing to 9, and then they move up 1. So you'll see here that we've got the number 1493. What it really means is we've got 3 lots of 1s. We've got 9 lots of 10. We've got 4 lots of 100 and 1 lot of 1,000. That every column is 10 times the previous column. We're so used to it, we don't think of it that way. We keep up jumping in columns of 10. And if we could work out that figure by saying 3 lots of 1 is 3, 10 lots of 9 is 90, and so on, and you'll arrive, add them all together, and you're back to 1493. It seems a long way to get me there, but that's because we use that system when we come to other numbering schemes. We're jumping in units, columns of 10 with decimal. In binary, we've only got 2 states. It's either 0 or 1. And that means that every column is just twice the size, not 10 times the size of the previous column. So we're going from 1s to 2s to 4s to 8s to 16s to 32s and so on as bits. So if we see a number 1011 there, it's not 1011. It's a binary number in this case. So it's 1 lot of 1 one lot of 2, there's no lots of 4s, and there's one lot of 8s. In other words, 8 plus 2 plus 1, 11. It's 11 in decimal. So how do we know the difference between 1011 and 1011 in binary? Well, you'll see that when it comes to binary, we put a B at the end. And often you'll see a D at the end if it's a decimal number to avoid complete confusion. So we're jumping up in columns of 2 with binary. I've got here a counter that can do that for us. A binary counter. And what it's designed to do, if I can hold it up, there we go. It's got this end. It's got a button you can press, and you'll see here that the numbers change. So you'll see there, I've got the 1, 2, 4, 8 right along. So 4 is lit up. So there's one lot of 4, nothing else. Press it again. I've got one lot of 4 and one lot of 1. So I've got 5. And you can go up and down. And that would be on a panel to let you set values, but just by pressing buttons. And what it does, although you've said 9 on here, what's coming out of the back of this switch, oops, which way? That way. What's coming out the back is actually the contacts for the BCD. Now you could use that. If I go back to 0, they'll all go off. So that only counts from 0 to 9, this particular switch. If you want to, they all plug together. You can slot together, and then you can put as many different numbers as you want and get out the binary pattern out the back. So that's a quick way in instrumentation, especially in the old days, to feed in numbers by finger. But what comes out is the binary equivalent of those numbers. You can still buy them. £3.71 in Rapid. Or you'll see below it, we've got one which is adjusted with a screwdriver. So the top one is designed to be in a control panel. The bottom one is designed to be tweaked and left, probably inside a PCB or a bit of strip board or whatever. So we can manually convert what we see in our heads as decimal to the binary equivalents. We use the concept of adding numbers quite a bit in pocket money kits. What we're looking at there is the kit for the lighthouse patterns. And it covers something like 30 odd UK lighthouses as a consequence. And what you do is you're going to connect links if you want to. So if these dotted lines represent link wires that are optional. If you leave them all out, then what happens is that pin 3 is pulled high via that 10K, pin 5 is pulled high, pin 7 is pulled high. So with no links, these 3 here are all high. In other words, 111. 111 in binary is one lot of 1s, one lot of 2s, one lot of 4s, 7 in other words. So with no links in, we've taken option 7. If you put all the links in, then it's every one of these 3 is low. So you get 0, 0, 0. And any combination in between. So by using links, I can create a binary pattern that's read by this PIC chip. And the PIC chip then decides, based on that incoming pattern, what flashing pattern do I put out on the lighthouse light. So we use that quite a bit. If you don't want to have pots and trimmers, and you're happy just to have wire links, especially when you're, in this case, you don't want to really have a rotary system because you decide which lighthouse you want and just hardwire the appropriate links. It's permanently there. That's EasyBus. Some of you have got EasyBus. And in EasyBus, every module has to have its own unique number, its own ID. And we use the exact same idea here. On this one, which is the input modules, you've got 8 options. So there's 3 sets of pins. They can take either high or low. In terms of the output modules, there's 16 different addresses you're allowed to have. So you've got 4 pins. In other words, a 1, a 2, a 4, and an 8. Add them all together, you get 15, right down to 0, which is your 16 different options. So this idea of using links, or in this case, jumper links, we can set up a binary pattern that's read by, in this case, an Arduino, or in the previous case, read by a PIC. So we're using binary, even when we don't really think about it. That gives you the idea. You could do a table which tells you what to expect as the outcome, depending on what the links are set to be high or low. So that's binary. Hex, a different kettle of fish. Hex doesn't work on base 10 like decimal, doesn't work in base 2. It works in base 16. In other words, the numbers go from 0 through to 15, in this case. In reality, there isn't a 10, 11, and 12 because you're back to decimal again. So what they do when they're talking about hex, you go from 0 right through to 9. That's your first 10. When you get to number 10, it's A. And the 11 will be B. And 12 will be C, and so on. As you can see in this whole row here, 9, 10, 11, 12, 13, 14, and at the very end you get 15. So if you see the letter F somewhere, it means 15. If you see the letter B somewhere, it's talking about 11 in hex. And you might think, well, why the heck do we have hex? What's the benefit? Well, again, the more you congregate and aggregate binary numbers, it helps intelligence. And let's see what I mean by that. There's a hex file. Those of you who've worked with PICs will know you write a program and you create a hex file, and that's the one that you use to actually burn the PIC chip. And it looks like that. In reality, there's no such thing as an F or an A. When you see F and A at the end of the first line, what we really mean is F has got a binary pattern of 15 bits that's got to go out there. And A that follows is a pattern of 10 bits. So it's a shorthand. If I had to show that in binary with zeros and ones, it'd be absolutely huge. Right? So we tend to use that as a shorthand. We're still handling it in binary, but we appreciate it in hex. Here's an example of a PIC program. So if you wanted to look, say, at, there's the hex contents of a file that we're about to, we've just read. It's much easier to see 2821 there than it would be to see a long collection of zeros and ones. Let's look at that a bit further then. So in hex, we get there by columns, not of ones, not of tens, but we're counting this time in 16s. So every column, the first column is the number of ones in the number, next is the number of 16s, the number of 16 times 16, the number of 256s, and the last column is the number of 16s times 16 times 16. In other words, how many 4096s are there? So let's work through this example. 10B9, it just means there are 9 single units. And then how many 16s are there? B, well, B means 11. So there's 11 lots of 16. So that this bit here actually means 176. How many 256s are there? Well, there's none. How many 4000s are there? 1. So 10B9, we just add these up and we'll get what it represents decimally. So 10B9 is the same thing as 4281 if my sums are right. But that 10B9 has got an H at the end telling you this is a hex number. But the same thing as 4281 decimal, which is the same thing as all of that written in binary. It's much easier to remember the binary or the decimal, sorry, the hex or the decimal than it is to read the binary. But the bigger the numbers get, the more the problem accumulates. There you go. If I split you guys up into 3 groups, and I said to the first group, your job is to remember A710B9, A710B9. And I said to the next group, your job is to remember 10,947,793. Who's got the easiest job of recalling it? And if I took the third group and say, your job is to remember 10100111, you've got no chance of remembering it. So when we're dealing with large numbers, hex even beats decimal. It's a shorthand way. That's a shorthand way of saying that's what's in the real world. Then the ones and zeros on the right are what you're actually really handling with. But you can talk about them in terms of hex to make it a lot easier to understand. Hope you get that idea. Right. If you get a number like 10B9, you can always very easily convert it back to binary. Because the number 1 on its own is 3 zeros and a 1, isn't it? There's no 2 5 6s, it'd be all zeros. B is an 8 and a 2 and a 1, this to get your 11. And there's 9 units, which is 1001. So we very quickly can reconstitute that if you wanted to know what it was in binary, simply by taking each number on its own and converting it into its own column. So we can jump readily between hex and binary and decimal to suit our own purposes. Bearing in mind, as I said earlier, that binary and hex are only numbering schemes. They're not what actually happens inside the electronics. Electronics is only, digital electronics is only concerned with zeros and ones. That's all it understands. If you're passing a number, it doesn't know whether that you thought of it as binary or whether you thought of it as hex. It doesn't matter. Right, so how do we pass numbers around then, which is the next thing. We've got numbers inside the computer and we want to move it from one place to the other. the early days, and still in some cases, are parallel. So I'm looking at a byte here. You'll see a byte of 10001. There it's at the top. We can send it all 8 bits at the same time. So that first line is carrying the 1, the second line of track is carrying the 0, and so on. And all 8 go at the same time. That was very common. You've come across it umpteen times. You know, things like this, the big Centronics printer cables. You know, they've got loads and loads of connections at the end, and big thick cables. But you're passing the data. If you want to print a letter, then you're sending the data in parallel clumps. Or disk drives, the pattern, the parallel ATA connection. Similarly, using the connections that Chick was talking about just last Sunday. They've got multi-pole and a ribbon cable. So this one's got, you can have up to 40 individual wires in this parallel setup. And we tend to use things in parallel quite a bit within, or we did rather, mostly. The problem with it is twofold. It was great at the time when it first came out, but as technology moved on and things get faster and faster and faster, then parallel handling wasn't as useful. It had limitations. Let's have a look. What were they? Well, 2 limitations. You'll see the little bit of red I've marked here. Basically, we're talking about crosstalk. If you've got lots of wires, 8 of them coming down at the one time, then, as you saw earlier, they're very, very close together. And therefore, if one's meant to be at a 1 and the other's at a 0, there can be leakage between the 2. And of course, the higher in frequency you go, the more chance you have, because if you transmit down that parallel cable at a high frequency, essentially every bit of wire going down there is like a transmitter aerial. So if we looked at the old technology, the Centronics cable was working at shifting megabits per second. But nowadays we want to handle hundreds of megabits and even gigabytes, sorry, per second, right? So that was one problem. The higher the frequency you go, the less reliable this becomes, because the incoming signal here is meant to be 0, but it might be leakage from the 1. And what arises at that side is something that can be recognized as a 1 instead of a 0. Crosstalk. And the other is what they call skew. It's a bit like saying, if I got all you guys to go on an 8-lane motorway and told you to drive at exactly 30 miles an hour, in theory, you should all arrive at the destination point at the exact same time. But in the real world, you know, some of you arrive a bit earlier, a bit later than the other. And that's the problem about skew. The faster the transmission rate, the more you have differences in the cable between inductance and capacitance and so on. And therefore, the 8 bits, one of them may arrive slower than the rest. And that means you would lose intelligence. So parallel fell out of favor in terms of serial transmission. So serial sound, well, that's odd. You think 8 at a time would be better than 1 at a time. But so serial works, taking the same byte, but instead of sending the 8 at the one time, it sends them like that, 1 bit at a time. And we're used to that all the time. We've used USB cables for everything, for your mouse, your keyboard, your printer, all kinds of stuff. And inside computers nowadays, you don't have parallel connections for your disk drive. You've got these SATA cables. And we're used to that also for things like network cables, as you see there. EasyBus, C-Bus, DCC, all are sending data serially. Because when we get to serial, we don't have the same problems of crosstalk or skew that we have with parallel wires, and we can go right up the latest spec. I believe we see USB 4 and Thunderbolt 3 are now talking about running at 40 gigabytes per second, which would just never ever work with a parallel system. Right. Next thing I want to talk about is data and information, which are not the same thing. Data is just the raw accumulation of all your bits or bytes, whatever. And information is what you understand them to mean. So there's an example. I've got 2 bits of data, 16.1, 17.4. Some of you may recognize that that was the result of a certain referendum. If we're using the data to mean votes, but it can mean different things in different situations. For example, if I can just pull up the next one. There you go. There's 2 other figures for the exact same amounts of data. 16.1 million people in the USA with major depressive disorder. And that was before the last election over there. On the other hand, the good news is 17.4 was a lottery jackpot over there. So we're using the exact same numbers, but depending on what we treat them, we get different understanding. I'm no football fan, but apparently that was the transfer fees for Alan and Oliver, whoever they are. And then other good news, bad news, you probably have heard the story of that woman who spent 16.1 million in Harrods buying all kinds of junk. Whereas down below, the Americans came to Prestwick and gave us 17.2 million for fuel for their planes. So I've just taken some ideas of 2 lots of numbers, and they mean different things in different contexts. Why'd I bother talking about that? Because that's exactly what happens in electronics. If I turn a knob on a digital system, say to 255, that probably means the local goes its fastest. But if I send 255 as a dot, a pixel to this screen, it probably comes up as a white dot. If I'm looking at the results from a light-dependent resistor, and I get 255, that's a level of illumination resulting from, or voltage resulting from that illumination level. If I send 255 to C-Bus or to EasyBus, it means different things. We send data, but it's to show that how we use it depends on what we're trying to achieve. You'll see, for example, in DCC, we have configuration variables, numbers that simply mean if you call up that number, it means go in reverse or go at half speed or a certain acceleration, a certain deceleration, and so on. And every DCC decoder must meet that basic spec for forward, reverse, fast, slow, lights, and so on. And therefore, they can be called a DCC decoder. But what happens then is manufacturers go beyond the standard set to offer extra things. If you pick mine, you get extra lights. If you pick mine, you can have sound. If you pick mine, you can have operate servos and so on. And the CV number to operate a servo in one person's decoder may be to activate a light in a different person's decoder. The same number means different things in a different situation. So let's just look up. So there's an old phrase about there's nothing new under the sun. How old is that, converting data into information? You hit the Morse key and you get da da dit dit da dit da da dit. In other words, wide pulses of tone and narrow pulses of tone and gaps in between. Morse code. Right? I'm sure you all recognize that. And depending on the pattern that you send out depends what the intelligence is. So what I just sent was MERG. That's merg in Morse code. Why am I bothering? That's so old technology. That's what it looks like in Morse code. A wide pulse of tone, da, another wide pulse, da, narrow pulse, dit, and so on. And I did say there's nothing new under the sun. So there's a pattern of wide and narrow pulses to pass information. There's DCC. Can anybody spot wide pulses and narrow pulses and gaps in between? We're using the exact same principle, obviously updated, but the data we're sending is very similar, just a bunch of narrow and wide pulses and gaps in between to pass over the information. We do it again in ASCII. When you're typing a letter, dear mum broke, send a £5. What you're actually sending out is a binary pattern from the keyboard, which is then understood by the computer and is stored on your disk. Once again, it's a binary pattern. So without knowing it, we're all using serial connections and binary every day of the week.